Okay, so we've just had quiz number 3. Today's class 19 out of 30, so we're about 2/3 of the way through the semester. We'll probably only get up to 5 or 6 quizzes maximum by the end of the semester, so that was 3. Your next homework assignment is due a week from today on October 30th. I apologize if anyone, I did get an email from one student. I accidentally set assignment 4C to close at 10 o'clock today instead of 11. So I fixed it, but maybe some of you, if you're submitting between 10 and 10:25, experienced some delay, and I apologize for that. This next one will be due at 11 o'clock on Tuesday, the 30th of October. I'll double check to make sure that the time isn't set wrong. So we're getting into chapter 5 now, and this entire chapter is founded around one pretty simple idea. It's just that we're going to be combining thoughts from earlier in the semester with this one simple but important idea. So homework 5A is due a week from today. All right. So the Oahe Dam, you can see here, an unusually flat surface in an otherwise very meandering and irregularly shaped channel. It's the 4th largest artificial reservoir in the United States, the Oahe Dam. It's damming the Missouri River. And the way that really large bodies of water are quantified is in terms of acre feet. And that might be a unit of measurement that you're not acquainted with. You're probably acquainted with units of volume measurement, maybe gallons or cubic feet. But when there get to be so many zeros at the end of gallons or cubic feet that it doesn't make sense to measure them that way any longer, they switch over to acre feet. And an acre foot of volume is kind of what it sounds like. If you had an acre of area and a depth of 1 foot, then that would be an acre foot. So then if you wanted to convert between acre feet and cubic feet, then what you'd do is, we know there are 43,560 feet squared per acre. So if you had 1 acre foot, then that means it is an acre of area and a foot of depth. So then you'd multiply this by 43,560 foot squared per acre, and then that would give you 43,560 cubic feet. So what we're saying is that this reservoir has 23 million acre feet. So it's a really large reservoir, and the primary purpose of it is flood control. Its primary purpose is just to try and reduce peak flow through the Missouri River and give the Army Corps of Engineers a measure of control in how much water is going through which part of the river at a given time. And so they can control the flow rate out through the dam. A secondary benefit of this dam and reservoir system is that it generates quite a lot of electricity. The value of that electricity is about $150 million a year. Oh, I'm sorry. No, that $150 million a year includes the electricity benefits and also the flood control benefits. So those are the combined benefits, of which some of it is the electricity that's being generated. Let's zoom in on the dam and take a closer look. Water flows through this dam in a couple of different routes. Now, first of all, there is an intake structure, and in ordinary circumstances, the water flows from this intake structure and through a penstock, which is just a fancy word for pipe that goes from a dam, and it goes to the power generation plant. And you can see there's these circular towers in the power generation plant. We'll take a closer look at that in just a minute. There are also some secondary release gates, and the need for these arises because the Army Corps of Engineers can't control how much it rains in the watershed upstream of this dam. And so they have a certain amount of water that can flow through this pipe and a certain amount of water that can pass through the power plant. But they envisioned the possibility that there could be unusually wet weather upstream of this dam, and they may need the ability to discharge even more water through these release gates. And so what we're going to look at is a video of just such an occurrence when there was a lot of wet weather in the watersheds upstream in the Missouri River, and they were maxing out the power plant, and then they also needed to open up the release gates. And here's a closer look at that power plant. It's a relatively low head dam, which means, this isn't the mountains by any stretch of the imagination. This is on the border of South Dakota and North Dakota. And so there's a little bit of topographic relief there, but it's not Colorado, it's not Utah. And so the difference in elevation between the reservoir and the receiving river downstream is relatively modest. We'll talk more about how to quantify the power generation capacity of a reservoir later in the semester, but one of the factors is how the height difference between the two. So you can see that the height difference is pretty moderate here, but still it can generate some electricity. Well, just to illustrate what we're going to be talking about in Chapter 5, let's consider this Oahe Dam and something that it experienced back in June of 2011. There was really heavy rainfall, as I already mentioned, and they had 160,000 CFS, and that's cubic feet per second. So that was the combined discharge through the power plant, and 110,000 CFS was going through these spillway release gates. Let's take another look at those. We can see that there's 1, 2, 3, 4, 5, 6 of those gates, and there's an interesting kind of triangular pattern that they're gradually opening wider to try and dissipate some of the energy as the water comes through the release gate pipes. There's a lot of energy there. When you're passing 110,000 CFS through 6 pipes, that's a lot of water. And we'll see that in the video in just a minute. Before we get too much into the nitty-gritty of the rest of these numbers, let's watch these videos. First of all, there is the Army Corps of Engineers kind of will tell you what their planned discharges are at various water bodies that they control. And so here's just an example of they have news releases on how much water they're going to release out of the Gauley River, Russell Fork River. And so at any time you can go to the Corps of Engineers and they make a lot of their data public on what the discharges are through their locks and dams. And so this is just an illustration of some of that data that's available. But really the exciting thing is to look at this discharge. And so let me make this full screen. And we'll go ahead and turn on the sound too, because it's kind of soothing, I suppose. All right, so 6 pipes, 110,000 CFS. So how much water is going through each one of those pipes? What's 110,000 divided by 6? Let me turn that off, actually. The noise of it. All right. We'll keep it rolling, though. So how much does it flow per pipe? 19,333 CF. How much? 18,000. All right. Thank you. 18,333 CFS per pipe. All right, so there's a lot of water going through there. They've zoomed in on one of them. See how the water's kind of spraying all over the place? That's a pretty good indicator that there's a lot of energy being dissipated there. The water's coming out at a really high velocity. What do you suppose the negative effects would be if that high velocity water was just allowed to go straight into the river? Erosion. Absolutely. Yeah, erosion. And the scour of sediment is dangerous not only for the aquatic species that live in the river, because there's a lot of particles and suspended clay and the soil is in the water, then it can interfere with the ability of fish to get oxygen that they need. So not only is it bad from an environmental standpoint, but it can threaten the safety of the structure itself. Like if you have a discharge of high velocity water just straight from the dam with no sort of stilling basin and no sort of like concrete armoring like we see here. So if you just had that immediate release in the close vicinity of the dam, then that scour could gradually cause the erosion right up to the surface of the dam. And then you have the threat of a structural failure of a really important piece of infrastructure. So instead of allowing that high energy water to discharge right into the river where it could scour the stream bed and damage the fish, or allow it to discharge really close to the dam itself, which then threatens that. So instead of that, they have this heavily armored concrete stilling basin where they're inducing hydraulic jumps. We'll talk all about the details of hydraulic jumps in 331 if you join me for that adventure. But needless to say, there's a lot of energy there that's being dissipated in kind of a controlled way rather than suffering the consequences in an uncontrolled, unplanned way. So we'll zoom in. The triangular shape, remember what we've talked about before. I just erased our number. You're going to need that later. 18,333 CFS per pipe. Okay. We've said already that Q equals V times A. You know, we used that formula when we were talking about Bernoulli's equation, where we had some pipe that's changing diameter and we have fast-moving velocity when there's a narrow diameter and slow-moving velocity when the diameter gets bigger. So back to the shape of these, it is gradually expanding. What's the velocity effect of it gradually expanding like that? It's intended to slow it down. So we start with this narrow diameter where the velocity is going to be high, and then as it widens, the velocity decreases. Now, it's not going to decrease very much when it's got this much momentum. But under lower flow rates, the velocity decrease could be more significant because there isn't going to be quite as much momentum as we see exiting right now. Now, every time I see this footage, I wonder, like, what if I jumped in? You know, like, what kind of a wild ride would that be? I guess I'd want a helmet probably, but maybe a life jacket. I'm a pretty strong swimmer. I don't know. Like, yeah, right. Yeah, it's not a cry for help. Me saying that isn't a cry for help. It's just, it's the thirst for adventure, I guess. All right. So let's watch the other one. I think it's essentially more of the same, but it's nice to watch videos of water. Okay, yeah, here's a close-up of the discharge. A lot of turbulence there. Just really violent. He was thinking about it. He just took a quiz. All right. So, let's get into the numbers now. We've seen the video. We have 110,000 CFS going through the overflow spillway, that emergency discharge, 50,000 going through the power plant. So that's not what we're focusing on. We're just focusing on the 110,000 through the 6 19-foot diameter spillway release gates. What's the water velocity through the gate is what I'd like you to calculate. So we've got this, Q equals VA, and we've already established that the Q the flow through each one of those pipes is 18,333 CFS. So let's determine what's the velocity under these real-world conditions that we know there's 6 of those pipes. Each of them is 19 feet in diameter. I wouldn't have guessed that from the video. They didn't look that big to me, but I looked it up, and that's how big they are. They're 19 feet in diameter. That's a big pipe. Okay, so what we need to do is take that diameter and turn it into a cross-sectional area. So we know that area is pi d squared divided by 4. So the cross-sectional area of this pipe is 283.5 square feet. And once we have that, we can find the velocity by just Q divided by area. So we found the Q per pipe, not the overall Q, because we've got 6 of these. So the velocity, this is the average velocity coming out of the pipe, is 64.7 feet per second. Now the rule of thumb that I learned when I was in school, and I think it's still more or less applicable, is that a concrete pipe can handle about 10 feet per second without any risk of it being scoured or eroded or pitted over time. So 10 feet per second is kind of a good upper limit for day-to-day use in a concrete pipe. For instance, like a sewer pipe or a concrete curb could handle about 10 feet per second before you have the risk of damage. So beyond 10 feet per second, then more careful attention has to be paid to the finish on the concrete, trying to make it as smooth as possible. More attention has to be paid to providing additional reinforcing steel in the concrete. So just there are a lot of different cladding and armoring techniques that can try and protect the concrete. And one of the big risks is cavitation. I think we've talked about cavitation before, haven't we? Anybody remember what cavitation is? I think we looked at a video, not a video, but a picture of like a Russian hydroelectric plant that had become obliterated. Bernoulli's equation, just to revisit this important idea, okay, so here's Bernoulli's equation, and we've got a reservoir, and the water is going into a pipe, and then it's discharging into a stream. So here's that river. So we've got water, and so what we just calculated is that the water velocity through that pipe is 64.7 feet per second. What happens to the pressure of a liquid when the velocity increases? What does Bernoulli's equation say the pressure response to an increase in velocity is going to be? The pressure decreases. Right. So if we wanted to apply Bernoulli's equation between, let's make this location 2 in the pipe, and location 1 is in the river upstream of that inlet pipe. So it's moving. It's not stationary, because this isn't a stationary reservoir. It's the Missouri River. It's moving slow relative to 64.7 feet per second. So we had some pressure at 1, and now the pressure at 2 is going to be lower, quite a lot lower because of Bernoulli's equation. And so the risk of cavitation is this pressure can go below atmospheric pressure. Like in terms of gauge, it can go negative. The pressure in the pipe can go negative. But when that pressure approaches the vapor pressure of the liquid, then cavitation is when the water is boiling, when it's going from the liquid phase into the vapor phase without any additional heat added to the water. You remember, we've watched videos of water boiling under a vacuum. So we know that one of the ways to make water boil is heat it, but then another way to make water boil is just to remove the atmospheric pressure that surrounds that liquid, and then the water will go into the vapor phase. And so what can happen in a situation like this is that the water's moving really fast, but then there could be these little bubbles forming. And bubbles aren't great because now you've got something that's going to scour the concrete even more, those gas bubbles, especially when they collapse, because eventually those gas bubbles will go through some sort of a section where the pressure is a little bit higher, and so those gas bubbles will collapse and then sends a shock wave through the water, a really high pressure shock wave that can pit the concrete that this material is made out of. And so there have been instances where pipes have failed for this very phenomenon that we're speaking about. I think I maybe have a picture of that failure later on, but let's see if I can find it. We'll skip right to it. Here we go. So this was just one of these same kind of pipes. Oh, I'm clicking on the wrong thing. There we go. This was a big pipe that was supposed to be carrying water from a dam, and it was moving so fast that those little cavitation bubbles started to form. Little tiny gas bubbles caused this huge damage that almost caused the dam to be threatened, and it had the risk of the dam itself failing, because this is scouring upstream towards the dam. So you can get an idea of how big these pipes were by the scale of the workers that are in there kind of trying to repair it. This happened, I think, in the spring of 1983, when there was a lot of rain in Colorado and Utah. And so, if I'm not mistaken, this is water that's coming out of Lake Powell through the dam there. I think it's Glen Canyon Dam, I believe. Cavitation risk is serious. And so what they do to get around that is now they inject air. I guess I don't have a picture of that solution. So what they do now to try and prevent the risk of cavitation in a situation like this is they inject a thin cushion of air that kind of protects the concrete. The water rides on top of that air cushion, and it doesn't have as much contact with the concrete surface itself. Kind of an interesting solution to the problem. All right, back to the continuity equation. We can quantify flow rate either in volumetric terms, where our units would be volume per time in terms of cubic meters per second or cubic feet per second. So here is how we calculate the volumetric flow rate. And you'll notice that here the V has a bar over the top of it. And that bar means the average velocity. Because the velocity varies at different locations in the pipe because of the turbulence. It can be really high in the center of the pipe. It can be lower, close to the edges. And what we need to have to find the volumetric flow rate is the average cross-sectional velocity. The mass flow rate is another way of calculating the flow rate through a pipe in terms of just multiply the volumetric flow rate by the density of the fluid. And then that will give you units of mass per time. So density, we know, is mass per volume. And if volumetric flow rate is volume per time, then multiplying density times Q would give you, in this case, kilograms per second. So mass flow rate is how many kilograms of a fluid pass through a certain location in a given time frame. So mass flow rate, m dot, is just density times volumetric flow rate, Q. Velocity distribution arises because of the difference in fluid resistance in contact with a pipe material surface. And you can see there's a bullet shape to the velocity profile. And we've looked at this in 2 dimensions before, where we said that at the center of a pipe, the velocity is going to be faster than at the edge of a pipe. So here at the center line, where you're further away from the location where the friction is trying to slow down the movement of the water. If the water is moving to the right, then the pipe is pushing on the water to the left. The frictional resistance is always in the opposing direction of flow. And so the water's moving to the right, and there's a lot of different velocities depending on where you are inside the pipe. And so the closer you are to the edge, the velocity decreases, and in fact, right here at the edge, the velocity is 0 because of the no-slip condition. But in reality, especially if we have laminar conditions where there is a nice regularly shaped curve there, what we can do is we can find the velocity at every location and multiply the differential area by the velocity at just a single location, where you can see that this circle has been drawn, and so we would assume that we have the same velocity at all points as we go around in that circle. If you have such a profile where you know the velocity at all points is a function of the radius, then you could integrate those differential areas with their respective velocities and find the volumetric flow rate that way. It's not usually how we do it, though. We usually end up with just measuring the average velocity rather than integrating the actual velocity. And that's partly because conditions are so rarely laminar. So the mean velocity then is what you've been calculating when we're in the lab, and you use the stopwatch and you see how much water accumulates in the wet well of the hydraulic bench. And so, with the stopwatch and a certain volume, you've been quantifying the Q. And then, just for example, when we were doing that flow visualization experiment where you had the little injected dye going through the viewing tube, the way that you calculated the mean velocity through that viewing tube was by dividing the volumetric flow rate by the cross-sectional area of the conduit that the flow is traveling through. In laminar flow, we have a relatively even distribution without a lot of variation due to turbulence, and that's what we see here, is that the peak flattens out in cases of turbulent flow to where the maximum velocity and the average velocity are pretty close together. And of course, there still is a reduction in the velocity at the edges due to the no-slip condition. So just to further familiarize yourself with the continuity equation and these definitions of mass flow rate and volumetric flow rate, let's say that we have oil flowing through a certain pipe, a 50 centimeter diameter pipe, and what we're given is the mass flow rate. We're told that there's 550 kilograms per second going through that pipe. So from that data, find both the mean velocity, so we're talking about V bar, and then also the volumetric flow rate, Q. Okay, so we're given the diameter in centimeters. We need to convert that into meters in order to calculate the cross-sectional area in meters. We're given the mass flow rate, so this m dot is 550 kilograms per second, and the density of the oil is 850 kilograms per cubic meter. Okay, so first of all, the volumetric flow rate, we can get that just by dividing the mass flow rate by density. So if it's 550 kilograms per second, then it's going to be 0.6471 cubic meters per second. That's our volumetric flow rate. And then to get the average velocity, we need to divide that volumetric flow rate by the cross-sectional area. So it's going to be 3.30 meters per second. Any questions about that example? Okay. There's something that's introduced in Chapter 5, the control volume approach, and it's a way of accounting for where mass is at a given time. And the idea behind the control volume approach is that if you have a certain area of interest, what you can do is keep track of the flow in and keep track of the flow out of that area of interest, and then it'll allow you to understand what's going on inside that area. So here in the control volume approach, what this illustration shows is that we have some pipe, and it's an irregularly shaped pipe and the diameters are changing, and this is still going to work even though we have an irregular shape. The control surface is the outside of some control volume. And the control volume is the location that we're analyzing during this approach. And so we have flow going in to the volume, and we know the velocity at this first location, which is the surface where the flow goes in. You can see that some of the control surface is along the edge of the pipe, and no water is passing through the pipe. It's not seeping out. And so these control surfaces on the bottom and the top of the pipe are kind of like passive because nothing's happening there. But then at 2 is where the flow is exiting our control volume at a different velocity. Okay, so there are some definitions that are introduced in Chapter 5 that we should be aware of. First of all, a system is defined as a continuously connected mass of fluid where the particles are the same property. So it's all oil, or it's all water, or it's some mixture that's homogeneous through that mixture. And the system is a fixed number of particles. And so how much mass is in what we define as the system is constant. Although the system's location may be varying, the system itself doesn't increase or decrease. The control volume is that space that we're going to be tracking the system's movement through. And the control surfaces is just the outside surfaces through which the system can pass. So their abbreviation CV we'll use as control volume, CS we'll use as control surface, and these same abbreviations will be important in Chapter 6 when we start talking about fluid momentum. Okay, so here's an application of the control volume approach, and it's best illustrated with a tank. And the reason why that's important is because it's a pretty typical storage location for fluids. And right now, at time t, what we can see is there's a certain amount of liquid inside the tank, and liquid is coming into the tank and it's exiting the tank. But the darker blue liquid is our system of interest. So it's a fixed number of particles, and there may be other liquid particles besides our system that exist, but we're not necessarily going to be keeping track of those other particles. And so you can see light blue in the inlet pipe and the outlet pipe. That light blue is just some liquid that's not in our system. You know, some pipelines can carry multiple fluids. The same pipeline that carries diesel fuel can also carry refined gasoline. It can carry a lot of different things, and they don't mix, not very much anyway. And so at any given time, the control volume approach could be used to keep track of different types of fluid as it moves through transport pipelines. And so right now, at a certain time, this is where the system is. The system is partly in the inflow pipe, and it's partly in the storage tank. But then at the next time increment, at time t plus delta t, the location of the system has changed. You can see that there's still some of it in the tank, and then now there's some of the system is in the outflow pipe. Look at the difference in the liquid level. At time t plus delta t, it looks like the surface is a little bit lower. There's less liquid inside of the control volume. And if we do this accounting, we can see why. Because more of the system is in the outflow pipe. The length of that, look at how long this segment of blue is compared to the amount that was in the inflow pipe before. And so what it looks like at first glance is that the flow out of the pipe was greater than the flow in during this delta time. And so the mass of system inside the control volume decreased during that time increment because the flow out was greater than the flow in. And so the water, or whatever the liquid is, it has two options in this particular case. It can, the incoming water can either be stored or it can exit. And The system itself, that is to say the number of particles doesn't change, but the location of the particles does change over time. So this is such a simple idea, the idea that what we're going to do is draw a line around some location of interest and start keeping track of what goes in and what goes out. But it's a really powerful idea that's used a lot in environmental engineering especially, where we want to know like concentration of pollutants as they become mixed into a river once discharged from a factory, or what's going to be the concentration of dissolved oxygen when wastewater goes into a river from a wastewater treatment plant. So there's lots of potential applications of the control volume approach. This is how we would express it symbolically. We say that the mass of the system at time t is the mass that's in the control volume and the mass that's in the inflow pipe. Whereas at time t plus delta t, the mass of the system was however much is in the control volume at this time, and now its new location is in the outflow pipe. So we can generalize that a little bit more into an equation that we'd use more often. What we can say is that inside the control volume, the change of mass is the change of mass that's coming in and the change of mass that's coming out. So in other words, we want to know what's in that tank and how it changes. Is the liquid level getting higher or is the liquid level getting lower? And so the change of mass inside this control volume is the difference between the in and the out. So think of it logically. If in is bigger than out, then that means the liquid level in the tank will be increasing. And so delta M would be positive if in is bigger than out. But if you have more flowing out of the tank than in, then the delta would be negative, and so the liquid level would be decreasing. So this is becoming a pretty generalizable and important idea. That is, the accumulation is in minus out. It's the same idea as your bank account. You know, like what's your account balance? Well, and how is your account balance going to change during a month? It's going to be the difference between the in and the out, plus any interest that you earn. So here's another way that we could say it, that the change of mass inside the control volume over time is the difference between the mass flow rates. So the mass flow rate in and the mass flow rate out. Now this equation so far is ignoring any sort of reaction that's happening inside this tank. And when you get to environmental engineering, for those of you who will take CE 351, you'll learn that, that there can be reactions that consume mass inside of a tank. Certain reactants can be consumed, and there are other reactions that produce. It depends on what you're keeping track of. You might be applying mass balance to a pollutant that's being decreased inside of a reactor. You may apply mass balance to a species of microbes that are increasing inside of a reactor. So this can be applied in a lot of different circumstances. But for now, we're assuming that it's a conservative substance and there's no reaction going on inside of the control volume. So we don't have a reaction term in this mass balance. Another idea that's introduced in Chapter 5 is that certain properties are related to mass and certain properties are independent of a fluid's mass. And so extensive properties are those that are proportional and therefore dependent on the mass of the system. So mass itself is an extensive property. Momentum is another one. Like we looked at the video of the water discharging from those big 19-foot diameter pipes. How much momentum is being exerted on the stream that receives that discharge is proportional to how much mass is coming out of the pipes. On the other hand, there are certain properties that are independent of how much you have. So, for example, the viscosity of a fluid isn't dependent on whether you have a liter or a cubic meter. So it's a property that's independent of the system mass. Color and extensive properties, once you divide by the mass present, can become intensive. And so extensive properties per unit mass become intensive. So we won't go into a lot of detail distinguishing between these two. There's some interesting text in the book that goes through it, but the main idea is that when a fluid goes through the control surfaces, the properties are transported with it. And so here, if there's momentum in that fluid, which is one of the properties that are related to system mass, the momentum goes through this control surface and it will have some effect inside of the control volume. So we'll talk a lot more about momentum in Chapter 6, but it's an important principle both in environmental engineering but also in hydraulic design. Okay, so with the remainder of our time today, we're going to do an in-class exercise where you apply these mass balance ideas back to the example of Oahe Dam. So as I give you this handout, this is something I'd like you to work on with your classmates. And what we're trying to figure out is how long is it going to take to drain this entire reservoir? How long would it take to drain if we used a certain discharge? We're keeping track of all of the in and out. And you can use your phone for the next, we have 12 minutes remaining approximately. There are some unit conversions in here that you may need to try and solve. For example, we have 13 million pounds of water per minute is coming from an upstream dam. And so you'll need to convert between million pounds to volumetric and so on. Okay, we know the area of the lake, and so here's our area, and we know the flow rate out is 160,000 CFS, and there are two streams coming in. One of them we can get just from Q equals AV. If we know the width and the depth of the river and its average velocity, then we get that the flow rate in is 1190 cubic feet per second. This other stream, though, it says that we have a certain mass flow rate, 13 million pounds per minute. So we have to convert the time scale of that from pounds per minute into cubic feet per second to be consistent with the other things that we have. And so we convert from pounds into volume by dividing by 62.4 pounds of mass per cubic foot. And so now we have a 208,333 cubic feet per minute, and then divide that by 60 to get cubic feet per second. So now we've got a volumetric flow in at 1, at 2, and the volumetric flow out. And the difference between in and out is what accounts for accumulation. Accumulation can be positive or negative. If we have negative accumulation, that means the liquid level is decreasing. And that's what's going on here. We have more flow out than is coming in. The net flow out, you can see, is 155,338 cubic feet per second. So there's a little bit of water coming in at these two spots, but they're dwarfed by this enormous flow out through the reservoir's discharge structures at 160,000 CFS. So the main question is, though, then how long is it going to take to drain? So we can get volume from the average depth. We already know the area, and it says that the average depth is 63.5 feet. So from the top view area, in terms now of square feet, and the average depth, we get the volume of the reservoir. So you can see what I said is the time to drain is the volume of the reservoir and then the net flow rate out. So 6.6 times 10 to the 6th seconds, which is, once we convert into days, it will be about 76.3 days. So there's some fun unit conversion in there, but the main big idea is maybe the simplest statement on this whole page. Accumulation is in minus out. That's the most important thing. All the rest of it is just conversions and number crunching in your calculator, but the big idea of Chapter 5 is accumulation is in minus out, and that's what we're going to continue with when we get together on Thursday. That's all I've got for you today. I'll leave this up for a few minutes if you need to copy it down. Otherwise, I'll see you then.